Power factor correction. What is the problem? On a small island, a power station needs to send power to a water pumping station. But power factor correction needs to be taken into account, otherwise it will cause problems such as reducing the lifespan for the equipment. Power factor correction is compensating for the current lagging by using capacitors to try and make them close to or equal each other. Power factor is the measurement of how effective the incoming power is. This is how the circuit looks before and after implementing power factor correction. Why is it a problem? It costs more money from power companies through tariffs and penalties. It can cause problems for the ESB's network. It can cause problems for the companies being supplied. It reduces lifespans of electrical equipment, and more power needs to be drawn, which increases costs.
Hello, my name is Samuel, and I'm going to be covering the calculation section of the power factor correction. On the left hand side displays the formulas in which were used to get the answer, which is displayed on the right hand side. We were given the values for the voltage source for 400 plus 0J and 50 fards. Our component of our line was 1.371 plus 0J. RL was equals to 7.5T plus 0J, and L impedance was equals to 13.9 microfards or millifards. We used the impedance formula: I multiplied by T multiplied by pi multiplied by F multiplied by L. The total impedance formula, which was the value of R line plus RL plus ZL. The overall current, which was done by Ohm's law, I is equals to the voltage source divided by the total impedance. The voltage across the load was calculated by multiplying the current by the impedance, and the imaginary power, we found the power and removed the real amount, so we were left with the imaginary amount of power. Once that was done, we then proceeded to find the power of the capacitor by dividing the value of the voltage across the load by 1 divided by 2 multiplied by pi multiplied by fards multiplied by the capacitance, which was then rearranged into the imaginary number or the imaginary power divided by the voltage source, by then giving us the capacitance of 1.788 multiplied by 10 to the power of 4.
My name is Richie Malloy, and this is my section for the Power Factor Correction Lab. I'll be covering the RC circuit and the money savings. This is the original RC circuit that was used. As you can see, we've found the resistance for the wires that we were given in question and added in the values for the resistor and the inductor for the factory. This circuit, when run in LT-Spice, shows out of phase from the supplied power and has a very high imaginary power usage. Its imaginary power being drawn is 7,120.8 watts. All of this being useless as it is wattless power and is just costing money to disperse. This is the corrected RC circuit, where we've added in a circuit and calculated its capacitance so that it should read more in phase, if not in phase. This circuit reads very close to the supply phase and has far less imaginary power being used, so it's costing less. The imaginary power being drawn in this circuit is 1,866.6 watts, where the ESB allows for a power factor of 0.95 before charges are made, and in this circuit compared to the original the power factor is 0.99 and would be within the allowances before ESB were to start charging. In terms of money saving, savings are made after the correction as power is now less out of phase and there is less imaginary power being transferred. There is a 73.79% drop of imaginary power after the correction, which would lead to savings as it was useless power as it was wattless, which still costed money to transfer, which is no longer being transferred, but the same useful power is being transferred to the factory.